Hey guys, welcome back. Hope all of you are doing great. So today we'll take our next topic, which is stability analysis. And in previous few videos we have skipped this topic. So what will be our flow? Whenever we start with amplifier design, we have been given with a device. Perfect. And that device could be your FET or your BJT, and what we have the S parameter of that device. So after getting our S parameter, we will ask one question, and that is if our device is unconditionally stable or not. If it is unconditionally stable, then we will go for the design. There is no extra work we need to do. And how we will know that our device is unconditionally stable? For that we have some necessary and sufficient condition, and in this video we will know them, like which are those sufficient and necessary condition. Now if your device is not stable, then we have two options. One option is to try to stabilize your device, and another option to accept that your device is unstable and go with a conditional stable design. Conditional stable design imply that for some matching circuit my device might go into unstable region. So we will avoid those combination of matching circuit. So these are the two options we have. If I do this, then I will transfer to my first option, like you stabilize your device and go with your design. But why we don't try to stabilize our device every time? Because if you do stabilization of your device, then there are some shortcomings are there, and for now we won't be discussing those things. We will discuss when I'll take up this topic, like how you can stabilize your device. So for now you forget this, and the main focus of today's topic is first of all to ask this question and mathematically get some condition will from S parameter will get us to know if my device is stable or not. And after we have decided, and if it is not a stable device, like not a unconditionally stable device, then we will develop some method by which we can avoid those unstable regions. So let's start. First of all, let's try to know why our device go into unstable region. In theory, anything unstable means something which, if we given some bounded input, then the output is going increasing and reaching to infinity, right? But in practical, we won't be getting in infinity, but what we get, it is some oscillation behavior from our device. And this is the method by which oscillator are designed. But as we are designing microwave amplifier, so we need to avoid this oscillation behavior or that unstable behavior. Now how we get this instability? See, from here, if I give some signal, perfect, and if I have a gamma in, then that my signal will be get reflected back with a gamma in, perfect. Then this signal will propagate in this direction, and again we have a gamma s, so it will again get reflected with a gamma s signal. So that means in input side I have a looping action. So if my gamma in or gamma s is more than 1, the magnitude of gamma in and gamma s are more than 1, then you can see we are getting an increasing action. Like if the initial magnitude of my signal is 5 and my gamma in is 2, then I will get 10 here. And if my gamma s is something also more than 1, like 2, then I am getting here 20, then 40. So like I am getting that definition, it is going on increasing. So that means if the magnitude of my gamma in or gamma s are more than 1, then I will come into a position by which my device will go into oscillation or in the unstable region. So that means the first condition, it should be my gamma in should be less than 1, my gamma s magnitude should be less than 1, and same things is true in my output part also. That means gamma L should be less than 1 and your gamma out also should be less than 1. And why less than 1? Because if your signal magnitude is 5, your gamma in is 0.1, your gamma s is 0.5 for example, or let it 0.1 only for mathematical simplicity. So after first reflection I will get 0.5, after second reflection I will get 0.5, then 0.005. So it is keep on decreasing, or my loop will die down. That means I won't be getting land into a unstable region. So for that we have 4 conditions, and they are this: your gamma s should be less than 1, your gamma l should be less than 1, your gamma in magnitude should be less than 1, and the last condition. And this is the equation for finding out your gamma in, and which is dependent on gamma L, and your gamma out is dependent on your gamma S. So keep this in your mind. And we know designing any amplifier means fixing your value of gamma S and gamma L. That means we fix this value. Perfect. So that means we will always fix this value less than 1. And after fixing gamma S and gamma L, we need to see our gamma in and gamma out, if they are in your less than 1 condition or not. So these 4 equations are your condition for stability, like unconditional stability. Like I can choose any matching circuit in input and output, and that will result in your gamma in less than 1 and gamma out less than 1. Moreover, from this we can deduce something else also. For example, let's take gamma in. Your gamma in could be also written as Z in minus Z naught and Z in plus Z naught. Magnitude, I need the magnitude less than 1. So Z naught is fixed to 50 ohm or something positive only, right? It can't be a negative number. So if your Z in is positive, then see the equation. Above we have minus, we are doing something minus, and below we are doing plus. So that means my numerator will be always less than my denominator. So that means the magnitude will always be less than 1. But if my Z in is negative, then always my numerator will be more than 1, like more than the denominator. So that means the magnitude will always be greater than 1. So that means this thing imply my ZS, my ZL, my Z in and my Z out should be positive always. And positive always means if they are complex, then their real part should have a positive term. Now what we'll do, we'll try to do one thing. Like from our flow we know if our device is not unconditionally stable, then what we'll do, we try to avoid the unconditional region. So to try to avoid the unconditional region, so to avoid unstable region, you need to see one thing. Your gamma in magnitude equal to 1 is the boundary. Like if this line is my gamma in equal to 1, that means one side I have the stable region, like it will be my gamma in magnitude will be less than 1, and another side I'll have a unstable region. So now what we'll try to get that boundary. To get that boundary, what we will do, we will take this equation and we will do it for gamma in, and same thing is valid for gamma out also. And For gamma in, what we will assume? We will assume that our gamma L is already less than 1 because gamma L is in our hand. So we have taken this equation and with little manipulation we come to this equation, and here delta is just a determinant of your S parameter, which is equal to S11 into S22 minus S12 S21. And why I am coming into this form? Because I want to draw the equation, a line equation or a something else equation which give me gamma in equal to 1, because I want to draw the boundary. And actually you will come to know that that equation will be a equation of circle only. Okay, and that equation of circle will be in respect of gamma L, like each point will give me some value of gamma L, and if I design my amplifier with that value of gamma L, then from that gamma L I'll get a gamma in equal to 1, because your gamma in directly coming from value of gamma L and the parameter of S. So we will try to do that, and to ease this work we have brought this equation into this form, because let me show you something. Why in this form? See, you see the equation A5. So you see this equation. Here this equation we have alpha, and alpha for us it is 1. Okay, let me explain you from here how we come to a circle equation. So you please follow me, and before that you just recall, like in my previous videos I have explained with you that if this is the equation of circle in the complex form, then from this I can come up to this A3, and both the thing are same to same. I have already derived them, and you can see from here also how they are deriving from this to this. Okay, so that means if any equation come into this form, then I can come into one conclusion that this is a equation of circle with center at Z0 and radius at R. So in this equation what we will try to do, we will try to get this equation into the form of this equation, and from that we will get out our Z0 to get the center and R to get the radius. So what they are doing here, they are squaring both the side, and they are doing everything just to get this into the A3 form, to this form. Okay, so they are squaring it, and squaring it means this, and you need to simplify it, means you need to bring your conjugate inside and then multiply them, and then cross multiplication will come up to this equation. Then they are bringing this side to the left hand side, and we are getting up to here. And then if you see your A3 again, we have Z square individually, and then we have first term, second term and third term, and then R. So we need Z square individually. So what they are doing here, they are to bring Z mod square individually, they are dividing the full equation with this term, and we are getting up to here. And from this you can easily see this is your Z0 or this is your center. So this is my Z0. And for R, if you know your Z0, then you can easily find out your R square using this equation. So this is your R or this is your radius. And everything we are getting here in term of alpha, A, B, C and D. Perfect. So that means if from this equation I compare my equation, and if I get the values for A, B, C and alpha. Alpha is already defined, it is 1. If I come to know the A, B, C and D, then from that transformation I can write what is my center and what is my radius. So this is our equation, gamma n equal to 1, 1 is my alpha, and I'm taking this same form as this equation here, as this equation here. So if I compare my A13 with my A3, then what I'll come to know that my A equal to minus determinant of my S parameter, V equal to S11 and C equal to S22. And if I know them, then I can directly write my equation for center. This is your equation for center and your equation for your radius, and this is, and you can see they are all in form of S parameter. Delta or determinant is also coming from your S parameter only. That means directly from S parameter you can deduce the circle equation, and these things are for gamma in. You can do same thing for your gamma out also. So we know now that how to draw that stability circle. And as I have said you, each point of my circle will give me some value of gamma L, and if I design my amplifier with that gamma L, then that will result my gamma in equal to 1. So that means it is on gamma L term, or gamma L is come for our output part. So that is our output stability circle, and we can do same thing for our input stability circle, right? Now see one thing, this is your Smith chart, and we have all assume that we know our center and the radius of our circle, and this is your input stability circle, and this is your output stability circle. Input stability circle will come from which equation? It will come from, input stability circle will come from this equation, because gamma S is here, and designing amplifier imply selecting your gamma S and gamma L, and you select gamma S in input part and gamma L in output part. So from this equation, don't be confused, like here it is gamma out, and we know gamma out is in your output part. Don't get confused. We decide input part and output part depending on our gamma S and gamma L. So this is input and this is output, and this circle will give me value of gamma S, which will result my gamma out magnitude equal to 1. Same thing with it, gamma L and gamma in, gamma L, I'm perfect. Gamma L and gamma in will be result into 1. Now this is the border. Now my stability zone is this side, this shaded side or unshaded side. So for that, what we can do, you just see one thing. In your equation of gamma out, let us go behind. In our equation of gamma out, what we have assumed? We have assumed that our gamma S is already less than 1, because we will select our gamma S which should be less than 1. Otherwise, from initial part only we are designing it for unstable. Okay. So what we have assumed? We assume that our gamma S is less than 1. We can also take gamma S equal to 0. Perfect. Because that will also result me in the stability, because for that I need only less than 1. 0 could be also be a solution. So that will bring out to me gamma out equal to S22. And if from my question, if my S22 is less than 1 and my gamma S equal to 0, gamma S equal to 0 imply that we are at origin. we are at origin, because here each any point could be our gamma s, and if we take any point in my circle, then that gamma s will result a gamma out equal to 1. But if I choose gamma s equal to 0, or which will be in my origin, then my gamma out is equal to S22, and if in the question S22 is given 1, less than 1, that means this is a stable region. So that means my shaded part, full shaded part is stable region, because this is my boundary, this circle is my boundary, one side should be stable. So as one point is stable, that means all other point will be stable. Now for other thing, if my S22 in question is given more than 1, then what is happening? If I take gamma S equal to 0, or in Smith chart it will be in origin, and if my gamma S equal to 0, then my gamma out will be S22, and as in the question it is given more than 1, that means my gamma out will be more than 1. That means that center will be unstable region. So at that time my this part will be only the stable region. Okay, and same thing is true for your output circle also. Now what could be the solution or condition for unconditional stability? Unconditional stability imply I can select my gamma as anywhere in this Smith chart. Anywhere, there is no restriction. So that imply if my S22 is less than 1, then what is happening? Let me clear it. Okay, so if for option 1, if S22 is less than 1 and I have a stability circle like this, then that means this side is my stable region, correct, and this is unstable region. But if anyhow I get a circle like this, or a circle outside my Smith chart, and origin I already know it's a stable part or point, that means my whole Smith chart will be stable region only. That means I can select any gamma s. So that means for S22 less than 1, my condition for unconditional stability is CS, which is your center for your input stable circle, and your radius and their magnitude should be less than or more than 1, because from here to here it is 1. You know na, that Smith chart from here to here it is 1. So if distance from my center to this radius, because if I get any center like 1.5, then how I will measure it? I will measure it from the center of my Smith chart to 1.5. So this is your 1.5. This minus your radius part. This minus your radius part should be more than 1. More than 1, why? Because I don't want to come inside my Smith chart. So this is the condition, and this is condition when my S22 is less than 1. If my S22 is more than 1, then the center of my Smith chart will be a unstable region, and that means there is no way by which I can get an unconditionally stable circuit, and everything I am speaking now, it's true for my output part also. So from previous condition, I can do some mathematical manipulation and I can come up to this. And these two are my sufficient and necessary condition for stability. And what is your K? K is your this. And you can see everything depend on your S matrix only. Your delta is also depend on S matrix and K is also depend on S matrix only. I'm not discussing about how we come up to this equation. And if you are interested, you can see this here, stability condition. But I would be suggesting you don't see it because it is really lengthy process. Unless you want to know it for some specific reason, don't go here because it's really little lengthy. So I'm just skipping it. So let us summarize what we have learned from this lecture. So what we'll do, after in question we get our S parameter, we'll try to find out our K and delta and we see the condition if they are stable or not. If we get satisfaction with this condition, then well and perfect, we can proceed with our design part, which we have done in our last video for unilateral case. For bilateral, we still don't know how to design. We will discuss them in later videos. Now, if it is unstable, then what we'll do? We will try to draw the input stability circle and output stability circle. So let us assume that we have already drawn them. This is for input and this is for output. Input means gamma s. So what we'll do, we'll select gamma s in such a way that it reside in our stable region. And how to decide on stable region, this part is stable or this part is stable, is to see how our S22. If in the question S22 is less than 1, then this is my stable region. Otherwise, that blank part will be my stable region. And for this output. And for output matching part, I'll see my S11. If it is less than 1, then this shaded part will be my stable. So I'll select gamma L in such a way that it will remain in this stable region. And if S11 is more than 1, then it will be in that blank region. Like I will need to select my gamma L in my blank region. Okay. And after that, we can like only this constraint, and other than that, we can follow the same procedure we are following in from our last videos. In our last video, when it is fully stable, like unconditionally stable, then we don't need to take care of like it is stable region or not. So this is the only fact like we need to keep on our mind when dealing with some practical circuit, because in maximum time our devices are not unconditionally stable, they are conditionally stable. So we need to keep these things into your mind. So this is the way how you do in your serenade. In your serenade, you need to calculate this thing, you need to calculate this thing, you need to calculate center to center, you need to calculate 2 radius because we have 2 circle. And then in Smith chart, manually using your compass, you need to draw them. And then you need to do your matching also. So in Smith chart, doing this little bit will take little bit time, but you try to do them. In our next video, like I won't be doing in serenade because serenade they are on manual calculation. So I think you can do it. What I'll show you in my next video, it is how we automate this thing in ADS, like how we give the S parameter to our ADS and how ADS bring us the circle automatically. And in your serenade, what you can do, you can use your MATLAB to do this calculation, as I have shown you in my last video how I am using MATLAB with my serenade to ease the calculation. Okay, So that's all for from this video. Thanks for your time. Bye bye.